Shall we get started? Blaine says yes. He's the boss. We're going to get it rolling here. So this session is, are smart pigs smart enough? And I'm the one that dreams up these smart aleck titles, so let me try to explain that a little bit. I think we've seen a rash of incidents around the country over the last, 5, 6, 7 years where there has been major incidents and it comes to light afterwards that, it was smart pigged a few months beforehand and the smart pig didn't catch what the problem was. I think Marshall, Michigan was like that a little bit. Mayflower, Arkansas was like that a little bit. The one that we became aware of because reporters started bugging us was one in Central California where a pipeline had a spill, a liquid pipeline had a spill in, I can't remember, in the fall, September or October. Turns out that it had been smart pigged. The smart pig didn't catch the problem. It was a seam, a corrosion along a seam, I believe. I sent the report to these three, so they'll probably talk about it more intelligently than I will. But the smart pig hadn't caught it. And it's kind of interesting because California has a rule on their books that says you have to hydrotest a pipeline every 5 years. And when you read their regulations, it's like every company has to hydrotest every 5 years. That's what it says. But because there's a clause hidden down farther below, unless you give us a reason why you shouldn't. And the reason why every company has said they shouldn't is because they're going to smart pig and use ILI instead. Well, after this first failure on this pipeline, if they had hydrotested, they probably would have prevented the failure that they had 6 months later on the same pipeline, almost in the same spot, which also had been smart pigged, and the smart pig hadn't caught it. And when they ran that ILI data through various consulting groups, including a proprietary thing from Kinder Morgan that's supposed to be like the best for catching different things, that analysis system couldn't catch it either. So finally, the California Fire Marshal ordered the pipeline to be hydrotested. So 2 failures in a row. Smart pigs weren't smart enough to catch either one. That's kind of what I threw to these 3 guys. Tell us why smart pigs are smart enough. So Ken Lee from PHMSA, who is the Director of Engineering and Research, is going to start off talking about this a little bit. And it looks like you're all keyed up there, Ken.
Okay, great. Thank you so much, Carl. Thanks everyone for staying and for your pipeline safety efforts and your interest in pipeline safety. So I'd like to start off by giving you some background. The U.S. has the oldest and most extensive pipeline system in the world. More people are living near pipelines. Pipeline mileage is increasing. And there's a lot of different pipelines we have in the ground. Diameter, wall thickness, grade, seam type, and there's many type of imperfections that we're looking for, that can cause the pipeline to fail. So we have a lot of challenges here. And so this is a map of the gas transmission pipelines in blue and the hazardous liquid pipelines in red that shows the extensive pipeline system we have in the United States that we all count on for delivering our energy, for our needs. Many of our pipelines are getting real old, as this picture illustrates. For our hazardous liquid pipelines, 55% were built prior to federal regulations in 1970, and for gas transmission pipelines, 59% were built prior to federal regulations in 1970. So a lot of these were built, pre-code, using different codes. A lot of them may have missing records and have other issues. And, failures may have many causes. This is a pie chart that shows gas transmission significant incident failures. And you could see there's a lot of colors here on this pie. And that corresponds to a lot of different types of imperfections that are in the pipe. And similar for hazardous liquid. There are many different causes of hazardous liquid significant incidents here. So. This chart shows, that the trend on the top shows that pipeline miles is increasing, but we see a decreasing trend in pipeline incidents. And we think that's mainly due to integrity management, and ILI is a big part of that, and trying to find these defects and make repairs before they fail. And so, this we feel is a good metric to illustrate. But as Carl says, there have been some high-profile incidents where ILI, missed the defect which failed, including Marshall, Michigan, Santa Barbara, and Carmichael, Mississippi. So in 2007, a propane pipeline failed in Carmichael, Mississippi, where 2 people died, and I've took an excerpt from the NTSB report there, where it says, current inspection and testing programs were not reliable to identify features associated with the long seam ERW failure. So there's also the 2010 Marshall, Michigan, which made significant national news with a significant crude oil spill, and the 2015 Santa Barbara oil spill, where the NTSB says ILI and subsequent analysis of ILI data did not characterize the extent and depth of the external corrosion accurately. So clearly, there's some issues which have been identified with ILI. And in the 2007 Carmichael report that NTSB wrote, they issued a recommendation to PHMSA. They recommended that we do a study, and that study shall include an assessment of the effectiveness and effects of inline inspection tools, as it applies to electric resistance welded pipe, which is a common type of line pipe, which is out there. And this particularly applies to low-frequency ERW pipe made before 1970, which is more suspect to welding seam issues. And so we conducted this study. We funded this research, and this is the web page. It's public. The web page is on the top, so you could access that. There are many reports. So this is one of the many research projects that we have to improve pipeline safety. And one of the many reports that came out of this is a track record of inline inspection as a means of ERW seam integrity assessment. It's a 2012 report by Kiefner and Associates and Detnorsky Veritas, and it identified significant weaknesses in inline inspection tools, including unreliable defect sizing, accuracy, missed defects, inconsistent failure stress calculations, and that more rigorous tool verification of tool performance is needed. So, we've been funding research to improve safety. Right now, we have a $12 million a year annual budget. We have an R&D forum about every 2 years. We had one last fall where there was a public meeting, and we invited everyone, to tell us what the top pipeline safety research needs are. And these are many of the past successes of the program, including on the top left, these robot pigs that can crawl into previously unpiggable pipelines, development of ILI sensors that could detect smaller defects. On the bottom left, you see SmartBall, which is essentially a ball with microphones that can listen for leaks as the ball gets pushed along the pipeline. On the bottom center, you see handheld tools for in-ditch inspections. And on the right-hand side, you see some leak detection, aerial leak detection methods, both by rotary and fixed wing. Many of them use laser that could detect hydrocarbon leaks. And there's improved welding technologies, and the list goes on. So this is one of the, I think, one of the more exciting things which we do, which is at the opposite end of the field than the enforcement side. It's not the stick or the punishment. This is the carrot on trying to move to best practice and helping the industry adopt these new technologies. And so here are some of the projects that apply to ILI tools. This includes, eddy current technologies, magnetic flux tools, EMAT tools, and also an ILI test facility to try to have a standardized method of testing these ILI tools. We feel that's much needed in the industry to try to advance the technologies and to help the industry get better. So as far as PHMSA regulations, we have comprehensive integrity management regulations, and ILI is an important part of that. And it's in our Part 192 natural gas pipeline code in Subpart O, and under the hazardous liquid code is in 192.452 under integrity management. And our regulations say that you must follow ASME B318S for selecting the appropriate tool for the covered segment. These ILI tools are generally used to find corrosion threats and other threats. And they're used to develop your baseline assessment, and then you have to run periodic assessments to see if the defects have grown over time. So, we recognize that, no tool is perfect. Each one of these ILI tools is designed to detect a specific imperfection type within a certain size and orientation. So, and all these tools, they're not perfect. They will not find every defect that's in the pipe. They don't have 100% accuracy. There's a tolerance associated with every tool, and that has been getting better over the years as the technology improves. And also keep in mind, this is an indirect assessment method. I think of it as looking at if you see a shadow of a duck, it's probably a duck, but it could be something else. It could be another animal hiding behind the duck. You don't know. So you need to do periodic digs for direct assessments to validate the results. You're looking at shadows. Was it really a duck? So I think we think one tool does not do it all. It's not a silver bullet, but this should be used as one of the many tools in your integrity management toolbox to safely manage your pipeline. So, another way to think of it as, the ILI tool is, one layer of defense. You need to have many other layers, to assess. Every tool has its strengths and weaknesses, and you need to use complementary tools to see things that, that tool may not see. So in summary, ILI is an important part of an effective integrity management program. You're much better off running ILI than not. You're much better off getting, more information than less information about your pipeline system. It's a very valuable tool. It has seen a lot of improvement over the last few years, and I think, everyone feels that it still needs a lot more improvement. We support new technologies to improve pipeline safety, including ILI, and this is illustrated by our strong research program which we have. And like I said, we support ILI as a part of a comprehensive pipeline safety approach. So I don't know if that answers your question, Carl, or smart pig smart enough, but this is helps discuss that issue.
Probe that at the end. All right. I think next up, this is thanks, Ken. I think Dave Chittick is going next. Is that true? Oh, okay. Jeff, we're going to need to swap computers because he's going to give us some fancy technology here.
Just leave it up.
Okay.
All I do is take this out. If I don't just shut the lid, I'll put mine on top.
let him do it because I'll muck it up. You don't want me anywhere near a smart pig.
Right, come on.
Login correct.
It was working. It's on the screen. Yeah, it was working before. Yeah,
Plug in here.
sure could have plugged in.
Okay, no problem. Let's just do,
Does need to be rebooted.
and that's computer only, right? So we just want to duplicate. Yeah, we'll just do that.
Yeah, that'll be good.
There, that should work.
Right. Right.
Smart people help.
Takes teamwork. Yay, success. Sorry about that little technical glitch. Although it does help with the presentation, because the presentation is about teamwork as well as tools. So today everyone's talked about ILI tools. ILI is not a tool. ILI is a process. And I want to just go through some of that. So for the people in the room or on the webcast that don't know what ILI is, I thought I would just do just a quick high level. It's taking measurements at 9 miles an hour. It's taking 120 million measurements a second. That's equivalent to 70 football fields of data being collected at each run. And 100,000 on 20,000 analysis screens. And finding a defect that's the size of a quarter. And the analogy I like to use is that of a medical imaging tool. Because what you're doing with an inline inspection is exactly what you do when you have your annual medical or biannual medical or whatever you do to make sure that you're okay. And if you find that you have an issue, then you go for repeated checkups and repeated images to see if that image or that illness is grown. So, why do we use inline inspection? It gets the measurements done from, all those measurements done from end to end of the pipeline, of the complete pipeline, not just a small part of it. It's a robotic device, which unfortunately is called PIGS, that's pushed down the pipeline by the product itself. So it's totally unintrusive. You don't know what's in there. It doesn't affect the flow of the energy. The pipeline still works while it's being measured. It can identify small flaws way before they become a big threat to the pipeline. Therefore, by repeat inspections, you can actually measure the rate of the flow growth and therefore plan your maintenance accordingly. It's the most comprehensive means of measuring the pipeline today. It's not perfect, but it is the most comprehensive. So if you look at the system, and I'm talking about the system here, the crack tool has A and B. A might be a piece of technology, B might be a piece of technology, or it may be a piece of equipment. Analysis, C could be an algorithm, D could be a trained analyst using that algorithm. And then we hand it over to the operators, and they have the pipeline integrity management engineers and the maintenance and repair people who select the digs and do the remedial work. So I'm not going to talk about that because Dave Chiddick from TransCanada is going to do that for us. So I'm just going to concentrate on the first bit. And to do that, I just thought I would show the small video of a typical MFL tool, just so people understand what a pig does when it's in a pipeline. These things you see that look like torpedo tubes in a submarine, these are launch and receive traps. This is how we get the pig into the pipeline. The pig has to be flexible. Number 1 rule, never get the pig stuck in the pipeline. Number 2 rule, make sure you get good data. So this particular pig uses magnetic flux. You see the blue circuit there going through the pipe. The sensors, the blue sensors in the center, are picking up metal loss and recording it on the tool. On the second module, we can see in the center some caliper fingers, which are actually taking the profile of any dents. The wheels on the back, they tell us where the pig is and how fast it's going, so that we can use it for location later. We were talking about on the mechanical damage before. We're talking about mapping the pipeline and being able to dig within a foot. I think a foot's a bit good within each state. A yard would be good, and the pig is recording that GPS data as it goes down the pipeline. On subsequent inspections, if we tell the center line has moved, then we know that the pipeline's under strain, because maybe it's a washout after a hurricane or something. Then we can tell that that something's going on there, that the pipeline's actually moved off its center line. So the first part of the process is for the operator to select the right tool and the right vendor. First thing is, not all our tools are the same, and not all vendors are the same. First of all, can you get the pig in the pipeline and out again without it getting stuck? Second, what is the threat I'm looking for? Am I using the right type of tool or tools? And then third one, what degree of accuracy do I want? What's good enough and what's essential? And if we look at this is an array of some of the early tools for looking for corrosion. We saw the video. We can use that in gas and oil pipelines. The next one, that's an ultrasonic tool for looking for wall loss in liquid pipelines. Very accurate. Then we've got a transverse MFL tool. We had to make that tool after a company in Canada had a failure along a long seam with corrosion. The original tool thought it was a series of pits. When they looked at the failure, it was a groove, what we call these days NAEC, narrow axial external corrosion, and it fooled the original tool's technology into thinking it was a series of pits. When we turned the magnetic field 90 degrees, we saw clearly that it was a groove. So for long seam weld inspection, for corrosion, then what we call the TFI or the CMFL tool is the tool for the job. And then at the end, we've got a geometry tool looking for dents and mapping the pipeline. So this is just one vendor's toolbox of tools, and actually it's just doubled with the acquisition of another company. But just shows you there's two choices of geometry, high res, low res. There's a number of metal loss tools, circumferential, transverse, or axial, magnetic or ultrasonic. And then you come down to the crack tools, and we have 3 different technologies there: piezoelectro technology, phased array technology, and EMAT, electromagnetic technology. So, just to give us an idea of how this thing's evolved. So how smart's a smart pig? I started in 1977, this is my 40th anniversary, for a small company in Britain called the British Gas Corporation Engineering Research Station. And we were targeted to find some way of maintaining the integrity of the biggest bomb ever created in Britain's history. 80,000 kilometers of high pressure gas pipeline under everybody's homes in a very small island. So our remit was, it must never ever fail, and you can never ever switch it off. So HydroTest was out. We had to find a means of doing it. Some smart American guys had been logging pipelines in the US called Linolog and Vetcolog, and we invited them over to a facility that we purposely built in the UK and put some defects in some pipes. And the interesting thing was, it saw all the defects. It couldn't size the defects, but it could see them. So we decided to increase the resolution by 100 times and create the first high-resolution tool. So that was way back in 1965. 1965 was when it all started, and 1975 was when the technology turned into high resolution. And if you go along here, you see that things like IMU, that's the inertial mapping unit, that's when you can start mapping pipelines. CMFL, I talked about that in 1997. As we found stuff, it evolved. It got smarter by either changing the technology slightly or learning more about it, or just making it faster, better electronics, better batteries, making it go longer. Along the bottom, that's the history of crack inspection. The same people, British Gas, way back in 1982, were worried about cracks in this brand new pipeline system. What if we've got cracks? How do we tell? So we created a tool called an elastic wave tool, and it got phased out in 2002 when the EMAT tool came along. And it was the only tool then that could inspect for gas cracks. In 1994, there was a company called Pipetronics developed the USCD tool, a very good crack tool in liquids. It was so good we bought the company, as the man said with a razor. And then we start to look at more advanced technologies like phased array, and I'll show you how phased array works in a moment, which allowed us to go from crack detection to crack sizing. And that's when we changed from giving bucketed sizes to absolute depth sizes with a tolerance. That helps the operators tremendously because now they've got a tolerance they can work on for selecting, prioritizing which cracks to go for. But going back to the point before of teamwork, it's not just the tool. I can go to Radio Shack tomorrow and build you a tool. There's 30 ILI vendors out there now. There was 2 or 3 when I started. But how many are reliable, repeatable, accurate? I was going to say certified, but we're not regulated, to give you the results that you expect. And the way to do that is training and experience. When an analyst comes in, he's not allowed to, or she's not allowed to touch real pipeline data for the first 6 months. Then they become a level 1, then a level 2, and then a level 3 is an instructor level. That applies also to field operators, not just the analysis people and project managers. And there's even an ILI PQ 2005 standard, which wasn't written, and ILI companies go, do we comply? We already had this and we went, are we compliant? And that is the minimum standard. We go beyond it. So over the years that we've run crack tools, we have found that there's at least 20 different types of cracks that grow on pipelines. Now, as an industry, we report 2 types, crack fields and crack lake. Crack field, that's SEC. That's pretty easy to tell. There's a whole field of cracks. There's not just one crack, so the tool can see it easily. On the crack lakes, then there's a crack lake in the body of the pipe, there's crack lakes in the long seams. Now, this is a weird pipe because I've got 3 seam welds in it. I've done that on purpose so that you can see the different types of welds and the different types of cracks that these coalesce to. Now, it's very easy to see stuff in the body of the pipe because there's nothing in there to give a reflector back other than the pipe. When you get around the seam weld, that's when it starts to become challenging. So, this is how the CD tool works. This is the phased array tool, but it works similar to the piezoelectric tool, except in this mode, it's doing wall measurement, so it can do 2 missions. You can see that each sensor carrier is slightly offset, so you get full 360 coverage. And this is pitch and catch, where we're throwing sound at 45 degrees at the cracks. So if you look at the evolution of crack tools from way back in the day. What I don't want to focus on is the individual tools on the top. I want to focus on the advances in analysis and the advances in reporting. When we first bought the USCD tool, it took 1 year to get a report. You ran the tool, you did some analysis, the operator did some digs, you did some calibration, you put it back into analysis, and then you give them the report. It took 12 months. That would never stand up in US regulations for discovery. So we had to fix that. And we fixed it by using automation and by training algorithms and by training analysis people to be able to do it more efficiently, to the point where we're at 30 days now. 30 to 60 for CD, and a priority scan on EMAT within 30 days. So, people talk about how smart are they, what can they see, what can't they see. The bigger the crack, the easier it is to see. Now, Marshall, Michigan was mentioned. I mean, that crack was 5 foot long, and it was 25% to 40% deep, but it was sitting in Nake, which was 25% deep as well. So when you dig into these things, the tools worked. We didn't overlay the data on top of each other and see the cracks and the corrosion. We had 2 threats, not 1. That was a big lesson learned for everybody. So the tool didn't get it wrong. It wasn't a miss. All the tools saw them. They just didn't put the data in the same place, or the operator for that matter. But it wasn't thought about at that time. So this is one of the things we've just reported in Europe with the latest crack detection tool. That crack is 1/2 inch long and through wall. That crack will not rupture the pipeline. It's what we call a SEPA. It'll leak. But that's the level of detection. So we mentioned EMAT, and we talked about the gas operators, and we've got Dave coming on next. And this is an EMAT tool. EMAT's very different to every other tool I've ever worked with, in that it's a bit like an electric guitar. When you hit the strings and then you've got your pickup and you listen for the sound coming back and it gets amplified. And those blue and yellow sound paths are the sound going around the pipe. The other thing is, the pipe is an integral part of the analysis system. We need to know the pipe, the wall thickness and the coating to make sure that we get a good EMAT inspection. And we're talking about electric seam welded pre-1970. There's an EMAT signal, a Bonnie red thing on the green, and here's an X-ray along the seam of an ERW pipe that it reported. That crack was 0.16 inches deep. So, come here to answer challenges, because Carl's going to be upset about this. We didn't answer the question. So what causes ILI to miss defects, as we call miss defects? First of all, simple, pipeline cleanliness. If a pipeline's not clean, if the sensors are smeared, you're not going to get data. So the pipeline has to be clean. How do we fix it? Extensive cleaning programs, and we have tools these days that we can use to simulate the inspection to tell you the pipeline's clean enough. Because everyone says, when's a pipeline clean enough? It's clean enough when you can inspect it. But you don't know that until you've tried to inspect it. It costs a lot of money if it didn't. Using the wrong ILI tool for the threat. We talked about Mayflower. They would never find that defect for the tool they ran. And I know because it was ours. But we didn't know what we're looking for. They didn't tell us what we're looking for. Operators need to work with the vendors. It needs to be a collaboration. It needs to be part of the process. What are you looking for? Why are you looking for it? If you're just ticking the box to satisfy the regulator, are you using the right tool? Because top box ticking does not work. It's a road to disaster. Run an ILI tool too fast. There are limits. 9 miles an hour is pretty quick. I'm no sprinter these days. I can't keep up with a pig anymore. But if it goes tearing down a pipeline too fast, you just can't take the data in fast enough. One of the biggest problems in the gas industry here today, on the utilities with low pressure lines, is that pigs run out of control. Even if you can get it in the pipeline, if you can't keep the speed within the limits of the tool, you're going to have a poor inspection. How do you know you've got a good inspection or not? Post-data checks. So after the pigs run, we have a flight recorder inside the tool, like we have on airplanes. And we look at everything that tool's done during the run, so we know how fast it's gone, and we know how many sensors have worked or have gone off or come back on again. Because it's no good just checking the tool at the end and saying it's all worked. We want to know what happened inside the pipe. No or poor dig verification. This is a hot potato right now, and I'm really, really pleased as I get to the end of my career that this is actually starting to happen. We never used to get dig verification data off operators unless it was bad news. Now, people are starting to give us thousands of defects. Thousands. We're building databases up that we never had before. We build these tools and we build the algorithms on artificial defects. Now we've got real defect in the pipe, under pressure, results. The biggest question now is, how accurate are they? And there's a big symposium going on about how accurate in the ditch, especially crack detection is, or internal corrosion measurements are. And the tool's actually better than the ditch equipment right now. Why is it better? Because it looks at everything the same way every time. It fires every 80th thou around the pipe, and what it is it's repeatable. It might not be right, but it always sees it the same way. Whereas the guy on the pipe, he could be anywhere. Make sure the end of the ditch is good and we get the feedback. Non-standard pipe, and I'm going to do a little bit on that before I finish. We are finding more and more non-standard pipe in the ground. It's old, as was said before by Ken. It was put in the ground pre-regulation, a lot of it. So when we find irregular pipe, we need to make a note of it. The operator needs to know where it is. We need to make a database of it. And you need to act accordingly because the tool might not work right in that kind of pipe. We need to understand it. You might need to run more and more technology. Complex features. Now, I already mentioned Michigan Marshall. That was what I call a complex feature. It was more than one threat in a coincidental position. So we're finding a lot of this stuff now. Cracks and dents. Gouges and dents. How did the dent get in the first place? Something hit it, or it sat down on a rock. So what's making it grow? So we need to know the crack exists in the dent. So that's another area apart from cracks and corrosion. Overlay the defect in iron. So there's software around now that allows us to overlay data. We started building combination tools, putting different technologies on the same tool to look for the same threat a different way. And we're developing some new technology to do that as well. And derive unique analysis methodologies. If you see something different in the data, train your analysts to understand and recognize that. And then some of the stuff's not even codified. There is no code at the moment for mechanical damage. How do operators have to treat it? How are we supposed to report it? How is the guy in the ditch supposed to report it? We're undertaking an initiative this year. In fact, we're going to run the EMAT tool and the MFL4 in the PRCI test loop that Ken mentioned, the pull test facility in Houston. And we're going to try to come up with a standard for mechanical damage reporting that we'll pass on to APA and make that a standard for the future. So, what do we mean by an irregular weld? Well, this weld, and by the way, it should look like that without the defect in it. But that weld was inspected with a CD tool. You can see the yellow and red and green paths of the sound. It never missed the defect. It called the defect, but it didn't call the defect anywhere near as deep as it was because of the sheer physics. However, an EMAT tool ran this pipeline and got it absolutely right because the sound's going around the pipe and not bouncing around. So I mentioned a crack and a dent in an EMAT tool, and this is what we're going to run in PRCI. The EMAT tool, because of its crucifix cross formation and the sound going around the yellow path, it doesn't know the dent's there. It just reports a crack. We superimpose over the top a super high-res caliper on the MF4 tool, and we know where the crack is, we know where the dent is, we know the cracks in the dent. And that's because the EMAT goes around the pipe and not bouncing around at 45 degrees. And that's what makes it unique. Now, we're talking about strengths and weaknesses. Why don't we run EMAT on everything? It has weaknesses. It's not as accurate as the CD tool is in real cracks on standard pipe, which is what it was designed to work in. So what we're going to do to fix it, how we're going to make pigs even smarter. So this is what's on the table right now. It's being sponsored by another company, a client of ours. And that's to look for the next generation of phased array tool. So the tool hits things and sees things. We're pretty confident we can get the POD right, and we can also use multiple technologies to confirm the PODs right, not just the one tool and the one technology. But those 19 crack-like features, how do we tell operators what those 19 crack-like features are? Because some of those 19 cracks are not injurious, have been there since the pipeline was built, and there's no mechanism to make it grow. So they could spend an awful lot of money digging it up just to note that. And then on the next inspection, see nothing's changed. That's one way of doing it. But wouldn't it be better if we could get three-dimensional imaging? Now we'll go back to my medical analogy. I work for General Electric Company. We make MRI machines. We have the software to produce that image. But I have to go back down the pipeline between 5 and 9 miles an hour and do it in one hit with multiple sensors. So I've got to derive a sensor that's going to do that to produce that image in that time frame and in a hostile environment. When I get all that information, I don't want to go back to a one-year reporting timescale, so I have to develop automated learning. We also supply the FBI with facial recognition software. So if we use that software and that software, all we're missing is the sensor, and we're developing the sensor right now with GIT. So we believe within 3 to 5 years, that will be a reality. Then we'll be able to tell people exactly what's going on inside the pipeline with that technology. And that's all I've got time for. I look forward to the questions later. Right, I just need to plug you back in. Hopefully this time it'll just go straight on. Right.
All right. Last up is Dave Chittick, who's the Director of Pipeline Integrity for TransCanada. And looks like that's it, but maybe we should start at the beginning.
What a concept.
The right button. How does it work? Oh, yeah, you're right. Getting too late in the day.
Yeah, okay. Thanks, Carl. Good afternoon, everybody. Dave Chittick, as Carl mentioned, I'm the Director of Pipe Integrity for the U.S. gas pipelines at TransCanada. And I'll show you a little bit of a little map of TransCanada in a second to give a sense of the magnitude of the pipe here. But I've been with TransCanada for 30 years now, and I've been the last 15 years working in the pipe integrity area. And also within my portfolio is a technology management program. We've had a program for over 30 years now, and we have one of our key focus areas is inline inspections. If I can figure this. Okay. I'll just quickly. So here's the TransCanada system. We've got just over 56,000 miles of gas transmission pipes up from the top of Alberta right down to the Gulf Coast there. With our Keystone system, we've got 2,700 miles of a liquid pipeline. And we're not quite 60,000 miles, but we're on our way to getting there. And we've got pipes from 2-inch to 48-inch, from 5 pounds to 2,400 pounds. We've got pipes from every decade. The average age of the system is over 50 years old. We're not, we talk about ILI technologies. We've pretty much run every technology there is available somewhere in this vast system. So I'm going to, this is a slide that highlights the various threats to the pipeline systems, and I'm going to spend a little bit of time going over each of the threats and talk to the role, as it has evolved, the role that ILI plays with each threat. And I'm pleased to see that there's 9 threats there, and the ILI shows up in 7 of the 9 threats. So, but we talk a lot. We'll start with external corrosion. We talk a lot about external corrosion. It is, has always been one of the predominant threats that we're concerned about. I mean, typically Steve talked earlier today, the first line of defense is your wall thickness. I always think of the first line of defense as the coating system, but it is the wall thickness. I mean, the more steel you have in the pipe, the more capacity you have for the corrosion to happen. But, historically, the pipes were coated in the ditch with a coal tar or an asphalt type coating system, and that, we evolved from that into polyethylene tape, now on to fusion bond epoxy, and we've been using fusion bond epoxy now since the early 80s, and fusion bond epoxy really has proven to be an effective coating system, and all new pipes now pretty much have that coating system. Next up, the next line of defense is the cathodic protection system. Corrosion is an electrochemical process. We impress a current along the pipeline system to impede the potential for corrosion. And so along the system, we've got rectifiers and anode beds up and down the right-of-way. And early approaches to managing corrosion were really focused on maintaining the electrical potential on the pipeline system. So, monthly we're checking our rectifiers, and annually we're checking the test stations. We have a test station probably every mile down the pipeline system, and then based on those, we take those readings annually, and then we do an analysis of those readings. And if we had lows along the system, we would go back in there and we would do some detailed surveys, close interval surveys, DCVG, ACVG, and then we process all that data and design how to improve the cathodic protection system and install more rectifiers or more anode beds, or sometimes we would go in and recoat pipelines. But that's how corrosion was managed initially. Then the ILIs came around, and Jeff mentioned, started at British Gas in 1965. For TransCanada, our first inspection was performed in 1975, and a pipeline up in northern Alberta. And Jeff commented there, the first tools were good at just identifying where there was corrosion, but it couldn't give you any information as the size or the depth or anything. But so you had to take that data, and then you had to do a lot of excavating of your pipeline. So really not an ideal process, but continued pursuing advancements of the technologies, and we evolved to have low-res tools, low resolution, could get a reasonable call on length and depth, and such that we could work with that data, work with assessment models, work with tool tolerances and that, and optimize our dig program. But today we've got multiple ILI vendors, and we've now got, I get dizzy here, we have high resolution, we have super high resolution, we have ultra high resolution, and the tools have just advanced remarkably over the years, and can detect pinholes, can detect, the sensors have gotten to so much smaller, the data gathering is so much more improved. So I got a slide coming up that I'll show a little bit about the accuracy of calling out corrosion. But corrosion-related incidents for pipelines previously inspected has become quite rare. But when an incident does occur, there's an extensive effort to understand what happened and what was the root cause of the incident. And over the last 10 years, there's just been an incredible advancement in sharing of knowledge between operators. So operators, we got a statement we like to say a lot, where we might be competitors on a commercial front, but when it comes to integrity, we're not a competitor. So we're sharing all of our information. We had a failure back in 2009, a corrosion failure, and when we had done the analysis of that and came to understand what it was, as soon as we figured it out, we were sharing that information with other operators. So operators have really gotten good at this. So That's external corrosion. I'll pass on internal corrosion. Good talk this morning about internal corrosion. Look, an area I like to focus on is stress corrosion cracking. And TransCanada, we had our first experience with a stress corrosion cracking incident in 1985 in Northern Ontario. And you know, in early days of managing stress corrosion cracking, you did it through direct assessments and pressure tests, and to a degree, some recoding. So anytime we would expose the pipe for a crossing or a corrosion excavation or something, we would inspect for cracks in the pipeline. And we also had other models to tell us where the risk was greatest. In those pipeline sections, we would pressure test. And pressure test was effective at if there were a flaw in the pipeline, you know, filling the pipe full of water and pressurizing it up to 100% SMICE would open up those features. You know, so effective at opening up, identifying the features, but really inefficient from a pipeline operations perspective. Pretty much have to take a segment of pipe out for 3 to 4 weeks to fill it full of water, do the test, and then, you know, clean it up afterwards. And one of the challenges with the test is it was just a pass or a fail. You know, you either had a feature open up or you didn't have a feature open up. So you didn't learn anything other than you passed or fail. You didn't learn anything about potential population of flaws in your pipeline. And the approach that was taken with that was you could do an engineering assessment and determine the size of a flaw that could exist in the pipeline to just pass the hydro test, and then use your models, and you would grow that flaw over time and determine when you needed to go back in and do the test. And the intervals would typically range from 5 to 10 years, but over 90% of the time you would do a test, you never would have a flaw, but you had no way to know there wasn't a flaw there, so it wasn't an optimal process. So very early on, we were quite keen to pursue inline inspection technologies for cracks. Jeff mentioned elastic wave. We were relying on elastic wave back in the early to the mid-90s and just couldn't quite perfect it. You know, good identification of the cracks, but we couldn't discriminate enough from it. So too many features in there. So late in the 90s, in 1998, TransCanada signed a contract with British Gas to build, to build the EMAT technology, develop EMAT technology. And that process proved to be challenging. It truly was a challenging process. And you know, TransCanada remained committed to it. GE was committed to it. Rosen got in the game as well. And happy to say that now we do have EMAT technologies, and we've now completed over 200 inspections with EMAT technologies on our pipeline system. So we've enabled an optimization of our programs and enhanced our management of the threats. Now that was for the gas pipelines. For the liquid pipelines, ultrasonic tools have been around, technologies have been around since the 90s. And so they've had the ability to run inline inspection tools. So we've got the EMAT technology. It's a great addition to the toolbox. I like Ken's slide of it's not a silver bullet, it really is a toolbox. And now with this tool, what we're finding is we're finding the tool getting used with other technologies. You know, Jeff pointed out at the end there, one of the things they're looking for dents is to run EMAT with a caliper tool. But liquid operators, including TransCanada, we've run the UT tools and the EMAT tools, looking to have the differing technologies to complement each other. So quite beneficial. You know, manufacturing, a little bit of talk there about the manufacturing process. More of an issue for the liquid pipelines, for the, you know, reference to the flash welded pipe. You know, we've got these pipes were formed in the mill. The long seams were fused. The pipes were pressure tested in the mill. They were tested in the mill, but you could still have slight flaws in the long seam that passed the pressure test. And then, but in a gas line, these features are more or less stable unless they're acted upon from, excessive pressure cycling, which isn't typical in gas pipelines, acted upon from ground movement, and we monitor for ground movement. So more or less stable for gas pipelines. Now, for the liquid pipelines, there's this pressure cycling happens, so there is more the potential there for those features to not be stable and grow, and the liquid operators will be running the UT tools and the EMAT tools to manage those. Construction talks a little bit about girth welds and wrinkle bends. An exciting advancement to do with girth welds. Some of the older pipelines, we're becoming more and more rare, but you'd have a slight crack in a girth weld from a dated construction, and you couldn't really find them with inline inspection technologies. You'd find them through your leak detection processes. But we had a leak last year, and we ran a GE tool on that, MFL4 tool, and we were quite surprised, not surprised, we were quite pleased is the better term, pleased to see that the GE process was able to call out the crack in the girth weld. It's not a common threat, but it is one of these threats that shows up once in a while, and it's typically leads to a leak. The other comment there on the construction, there's a reference to wrinkle bends. Back in the 50s, early, late 40s, 50s, the means by which pipes were bent could induce slight wrinkles, ripples in the pipeline. That was the common construction practice at the time. Again, these features are stable unless they're acted upon. Now, we've had one incident back in 2003 where it was a ground movement near to a wrinkle bend, and that resulted in an incident. But we've now have a program where we're running MFL tools and caliper tools, and we have an assessment criteria by which we look at all of these wrinkle bands, and depending if you have a wrinkle bend associated with a long seam, we'll excavate it. Depending on the magnitude of the wrinkle bend, we'll also excavate them. So, by and large, stable threat. Third-party damage, that's good talk about. It's the number one threat to pipelines. It's not the number one threat from a from a frequency perspective, but it is the number one threat from a fatalities and an injury perspective. So, we are strongly focused on our public awareness programs and one-call systems, making sure people know about the pipelines, contractors know about the pipelines, call the one-call systems. We patrol, frequently patrolling our right-of-ways. One of the things we're looking for is where are there areas where there's potential for there have been some unauthorized activities. But also there's the reference to the ILI. So when we're running, typically running an MFL tool, we'll also run a combination tool. So we'll run the MFL for corrosion, and we'll put a caliper tool together, and we look at the dents that get identified in that report. And for third-party damage, you're looking for a potential for a topside dent. So there's typical response criteria how to respond to those. But one of the issues with dents is the potential for there to be a crack to develop in a dent, or a gouge to be in a dent. And Jeff talked a little bit about that. We've been focused on this for a good number of years. And we have our technical support team that developed a process doing a strain analysis and then a detailed analysis of MFL data, and are pretty confident that this process, proven it's out that this is an effective way to identify when there's the potential for there to be a crack or a gouge in a dent, and we respond that appropriately that way. Last up, this is a good hint here. The party's about to start. Weather, the last one here, weather outside force. We're looking for where we've got slope movements, the pipe and the soil interaction as slopes move. So historically, how we did that was we would monitor the movement of slopes, then we would model how the slope moves, how it can be pulling on the pipeline, pushing on the pipeline. We'd do the strain analysis, and we'd have acceptance criteria, and then we'd go in there and we'd excavate quite a complex process. We'd excavate an entire slope to allow the pipe to rebound. But oftentimes you'd go in and you'd do that exercise and find the pipe isn't where you thought the pipe was. You didn't need to do the exercise. But now we're able to run ILI tools, the IMU type data, run-to-run type comparisons. We can see how the pipe has moved. Also from individual runs, you can calculate strain in the pipe from an inspection. So we've improved upon that process. So just kind of some general trends. I mean, the ILI technologies are used extensively throughout our processes. The technologies continue to evolve and improve, providing more insights into our pipelines. We're integrating more data together, running multiple tools, multiple technologies, integrating the data. We're very advanced in implementing a toolbox that all of our data sets come in together, and it's rather challenging to bring a bunch of data sets together and align them, and you need to stretch them and rotate them, but we're quite advanced with that process, and so you'll be able to see if there's corrosion and a crack interacting, and we're quite pleased with that process. But I'm going to have a slide here, just talk a little bit briefly about technology development. So, in this space to do with furthering ILI technologies, I mean, the ILI market is quite competitive. I mean, Jeff mentioned there's 30 vendors there, and I'm sure every one of them is out there trying to build a better tool, a better technology, and we're quite a lot of opportunity there. A lot of research goes on. There's industry-funded research. There's research here, like with the Pipeline Research Council. A lot of operators are members of the Pipeline Research Council. We all pay a subscription fee to PRCI, and that money's pooled together and undertake a number of projects. One of the things, a recent development at PRCI, I mean, specific for the ILI, is the development of this technology development center in Houston. And in this facility here, there's test loops, all sorts of pipe samples, test loops, pull rigs. We can run the different technologies to prove out how these technologies are. Build a loop with different types of features within the pipeline, and quite a development, and getting a fair bit of use. Well, I got a couple slides here just from, I mean, we've seen a good number of slides from GE and Baker Hughes. There are a few other operators out there. Rosen's got very involved with research development. They've got an innovation center in Germany. A lot of engineers and scientists over there. Focusing on areas like multi-diameter tools, combination tools, putting multiple technologies together onto one tool. TDW is another vendor. This is a slide that just illustrates the different technologies and really focusing on where it's the overlap of the technologies and how we're benefiting from that overlap to identify gouging, cracks, and stuff like that. And same here, different technologies all on one peg. That's a caliper and a low field MFL and a high field MFL and a spiral MFL, and that's 4 different technologies all on one inspection. But I got this is a slide that's been around for a little bit. I like this. Thought I would share this with you. It's called the Running Man. So this actually was a TransCanada pipeline with a Baker Hughes inspection, and that's the signal that the ILI data analyst sees. There it is there. Does kind of look like Jeff was saying, he used to be a runner, but he doesn't run as fast as the pig anymore. I think that could have been Jeff. You know, there's the, you know, we've excavated now, coating's still on. That's what it's looking like with the coating on. That's what it looks like after we've, you know, cleaned up the pipe. That's what the laser scan of it showed, and put them all together. So, kind of a good story there. But you know, kind of to wrap it up here, you talked about the important role that ILI is playing in managing the threats to our pipelines, and how technology has improved and how it will continue to improve. You know, we talked about it is a process. I mean, there is standards, there's regulations, there's processes to qualify tools, processes to verify, to calibrate. It is a process. It's not just tick the box. So are tools smart enough? So I think the ILI tools are smart. You know, today we've improved and found ways to benefit from the tools. The tools are getting smarter and smarter. I take great comfort in understanding how advancements in tools are going to help improve you know, the job we have of managing the integrity of our systems. So that's it.
So we have time for some questions. Any questions? Let's start over there.
First, I don't want to monopolize. I got a hard question to ask. So, if you want to take it, I'll be happy to lay it out on you. I've come to this, you know, from the outside. I'm an inside the fence guy. A lot of pipe, but all inside the fence, and ILI isn't part of my world. So I came to this and looked at the data, and I get quite confused. I wrote a paper last spring that I presented at the NACE conference on a modeling pitting corrosion based on a suggestion John Kiefner made. And what was interesting that I found is when I went looking for data to calibrate my model in the open literature based on ILI through the life cycle of a pipeline, there is just one good data set in the open literature, and it comes from Pemex. And it comes through the University of Mexico, and Francisco Caleo and Elma Valor done some beautiful academic work on that data set. It's about beat to death. And I am very interested in getting more data into the public literature so that the general community can form some kind of an impression about what this technology can really do. There are all kinds of claims made. I'm sure within the industry you share a lot of information, but at least in the U.S., the academic community has very, very little to work with. And they're the ones that build your credibility over the long time. Now, there's definitely some issues. In our area, an operator recently made a claim about what you can find with your CPCM tool. Stood up and made it ironclad. Sounded like he knew what he was talking about. Turned out to be dead wrong, as found by actual inspection. And when that happens, when that stuff starts to pile up, it undermines the credibility of your industry. Now, your industry is absolutely critical to keeping our old infrastructure running. We got thousands and thousands of miles of pipeline out there with failing coatings, ever-increasing number of features, and patches all over the thing, 15 a mile some places. And that's got to make inspection very difficult. And so the question of what you can really find with these technologies, and there are many, many, and it will continue to evolve, it really is difficult in the sense that if you had to go into a court of law, you would be in a mess, I believe, trying to say this proved that. In the chemical world, we have all kinds of validated methods that have been beaten to hell. And they're the gold standard. If you take them into court, everybody believes you. This industry, I think, is headed for a crisis, given the aging pipelines, some of the claims that operators are making for what this technology can find, and the lack of any really validated information about what these technologies really do. When I went to look at what I could find about what the CPCM tool would find as far as its detection limits and things like that, there's nothing there. I couldn't figure out what it did. So I guess this is just a comment that your industry, which is critically important, I would recommend you start to share enough information with the academic community to build your credibility. And there are probably many avenues where you could do that and where the data sets could be laundered in such a way that they wouldn't indict any particular operator. But this is something that I think the industry needs to be thinking about very hard. Thank you for letting me make the comment.
Anybody want to touch that one?
Told you it wouldn't be easy. You have time for a drink.
I mean, I think it's an interesting thing. I kind of understand why there's not a lot of public data available. Is there data available to academics or even to PHMSA? Does PHMSA have data to?
There's not, because contractually, it's the intellectual property of the operator, right? But the comment I was going to make is, I think Alan mentioned it earlier today. There's a working group in Washington starting. My boss has actually just been put on it. Bryce Brown in the room for Rosen, he's on it, about data sharing, and it was based on dig verification and learnings between operators and ILI companies on, when it comes to safety, we're not competing type of ground with, and this happens in the aviation business and the nuclear business. It's never happened in the pipeline business. One of the reasons is there's 30 vendors, there's thousands of operators, so getting consensus is difficult. But there is this plan to try and share more information. I think it was designed mainly for the industry, but it could be extended to academia if it was vetted properly, for sure. I mean, no one's trying to keep it a secret. I think it's just competitiveness of the industry makes it difficult to share if you're not inside the industry.
But, you know, there are conferences. I mean, there's the ASME every second year. There's the pipeline conference, and the information available there is quite considerable. You'll find all sorts of papers, all sorts of data on corrosion, on cracking, on manufacturing. There's no shortage of information available there.
Well,
So
I disagree on that, and I think I have a copy of every paper on pitting corrosion ever written in part of my literature survey for the paper I published, and I found a great paucity of complete data sets that where one has not only for pitting, which is the simplest really, guys have been looking at that a long time. A lot of times you might see a very broad distribution of pit sizes, but not the aerial pit density, so you don't know anything. It's a lot of that kind of data. The only set I found that's complete enough to work with to build a model was that PEMEX data set.
Graham, did you have something to add?
Yeah, I was going to weigh in on a couple of points. I'd first like to repeat something Walter Kresek had said at SEPA Incident Learning Forum a few weeks ago, that if you're interested in expanding your data set around ILI verification, the ND, what you find in the ditch versus what we found with the ILI, then Enbridge is more than willing to share. So reach out to me. I can help set up. But or if you know Walter, then give him a call directly.
No, I certainly don't.
So, but the other comment I'd make is I think it's unfair to characterize that there isn't academic involvement in the science. I think the academic community has migrated to where it can most efficiently work with pipeline companies, and that's in places like PRCI and CFR. A lot gets done through joint industry partnerships, and it's not about being closed, it's about expediency. We don't have time when you look at how, when you look at how much things have changed in terms of the technology since 2010, then, I mean, you don't have time for 3 years of research and then wait on a paper. No, we want to make these continual improvements year after year after year. The academic community is working within the vendors. It's working within, well, it is within universities as well. But it's just not open there for anyone to download because it would be very, very difficult to even characterize what's being put out there.
Well, I'm
So-
looking for things that are published by ASME or such organizations, real publications by real scientists that have gone through peer review, things like that. So, I just don't find it. And I was surprised because in many fields you can find very large data sets released by the industry that give the researchers something to work on. It isn't online stuff. It doesn't affect the continuous development of technology at all. That's going to go on, and that's commercially driven. I'm talking about the people that are trying to drive the science.
Yeah.
And that happens offline, and it needs good data to happen. And in this area, it's very hard to find.
I'd say 3 of the people driving the science right behind you.
I hear you.
And
GE in particular, come on, you guys are the 1,000-pound gorilla here. I guess I've said enough, but it certainly isn't a very difficult thing to do. Data exists. All somebody has to do is put it together and file off the serial numbers, and it's good.
All right, other questions? Mr. Cooperwitz.
Well, I'll just make a statement that it isn't that complicated to get your POD and POI for your particular technology. You can sterilize it by the company, whatever. We had to do that after the Bellingham tragedy. It became in that Washington State. Those reports were a matter of public record. We didn't, go down to the vendor or whatever. But we needed to give confidence to the people who are going to have to live with that advancing technology. And we want pigs to work. Don't get me wrong. I'm not here. I'm not anti-pig. I want to be able to say this thing works. But if I've got to stand in front of a bunch of families that have lost their victims, their family or their kids, and tell them, well, we made a mistake because we didn't integrate the data, that's a tough place to be. So you've got the capabilities. I know you're doing thousands of field verification digs. There's ways to get that information out. You can look at what was going on in Washington State, 15 years ago. There's ways for you to get that out there to reinforce your positions and your advancements, to gain the public's confidence. Without that, you're going to get resistance. And there's lots of projects with multi-billion dollars behind their numbers that are getting resistance because people don't believe you. And yet, if you've got a good story, you ought to be able to convince it, not just in marketing, but you can demonstrate it in a way that'll allow you to move it forward. And I'm sorry for the speech. I don't need another Bellingham, all right? Excuse me.
So I see films of people in the room, and maybe Ken can answer this too, because my understanding is the Voluntary Information Sharing Committee that's been stood up is a lot of that is based on how do different vendors start sharing this stuff so there can be comparisons.
Yes, thank you for mentioning that. Yeah, we have on our website a number of voluntary information sharing meetings, and this is to encourage industry to share data such as this, to move industry forward.
Just last year, we undertook a PRCI project. FIMSA put $1 million into this test facility, and GE and TDW were 2 companies that put their hands up and actually did the test. And the test was a very extreme test. It wasn't just, this is a little pit and this is a bit of corrosion. This was real pipe that had come out the ground that had issues with ILI, perhaps. And we had to prove that we could meet our specification. And it was successful. But that paper is with PRCI. You can purchase it. But there was a lot of, well, no, because it's a test and we want to encourage other people to go in and prove the tools too, we didn't want to divulge what all the defects were. So there's a company called Blade Engineering who are the only ones who...
Yeah, really don't get your story out.
And the guys in
That's why we took part. We want to get that story.
The guys in Schenectady decided you said
Alan, go ahead.
Mentioned a couple of times, and thank you, Carl, for bringing it up, but related to the Voluntary Information Sharing Working Group, I'm really excited about that group, but you know, what we've seen over the years is, you know, a common refrain in the aftermath of an accident is, gosh, I just ran a tool 3 months ago, and we just missed it, and we got it almost right. I mean, there's a lot of good work being done related to running tools, but we want to get it right. We want to get it, you know, so that we need to be better at picking up these defects. It's always easy to look in hindsight. There are a lot of challenges to that, and I think that's where this VIS working group can really help, because there are issues of, you know, commercially sensitive data that we just can't seem to get around to really truly compare information as it's needed. And this group will look at how do we get around that issue, proprietary issue, legal issues, to having a system where you can share information without worrying about that, because that seems to be one of the big gorillas in the room with being able to adequately share information and the performance of tools. Because, you know, that there's a sensitivity related to that, and there's an ownership, you know, a lot of intellectual property involved. We've got to find a way to work around that. So I think it was right for Congress to call it out by name. Specifically, they identified ILI to be addressed by that group. And I think that'll be, of course, I think of it as the basis for other things as well for sharing information. But so I'd say stay tuned. We do have, I mentioned the meeting coming up. It is open to the public, although this next meeting, the focus is going to be developing the mission statement and the direction. But over the next few, you know, we'll make sure it's on our website, it's posted when those meetings are held. So I would encourage, you know, people to come and watch. Thanks.
So I'm standing in between this group and beer, which is not a good place to be. But I'll at least ask one more question, because I thought I asked a fairly simple, although probably naive question. Are smart pigs smart enough? And I'm not sure I ever heard an answer. And I think the answer I heard, and correct me, is that maybe. Because a lot of what you talked about, you know, is it the tool that's not smart enough? Is it the analytics that aren't good enough? Is it human error that messes up somewhere along the line? And in some of the examples you talked about were human error. It wasn't the tool itself. The case I gave you in California, you know, the fire marshals couldn't seem to come to a conclusion about what the problem was there. So is it a little bit of everything, and as the tools get smarter, we should see the incidents going down?
Well, in my 40 years of being involved in NTSB or whatever, there's only one occasion where a tool has not seen a defect. That means the process failed. That means it was a human error, or it was never seen before, or it was complex. And the one I mentioned that a tool never saw was the Dixie pipeline. And that pipeline, PHMSA themselves, sorry, not PHMSA, NTSB themselves couldn't determine where the point of origin was on the pipe. And definitely in the data, we informed Dixie of numerous seam line cracks. We did fitness for purpose on them. They removed them from the pipeline. They were quite substantial, and they didn't fail. But this pipeline failed. And when you look along when you do the forensics, you can usually see a chevron marks where the pipe's initiated and it's run. Nothing along that seam weld. And it remains an anomaly. I mean, NTSB actually come up with the girth weld field and it ran along the seam weld. The industry don't agree with that. And personally, I think the pipeline moved. But, and maybe it was initiated in the girth weld, or it was a huge spike and a movement at the same time, because more than one thing. Like in every pipeline failure, it's more than one thing. But other than that, I would say the tools are good enough. The process needs to be good enough, and you learn by your mistakes. That's a part of the information sharing. I think that's where it's going. Is, you know, let's not two vendors make the same mistake with the same defect, which can easily happen these days. The industry's more open now than it's ever been. The operators are more open. The vendors are more open. We wouldn't even be in the same room together at one time. So, you know, I think the intention's right. Are they smart enough? Yes. The application, you need to be smart with the application. The tool does what the tool does, and it'll do it reliably, and it'll do it repeatedly. Make sure you've got the right tool for the job, make sure you're applying it properly, and you've got the experienced analysts to give you the right result. That's my answer.
All right. Last words of wisdom. Linda's going to get the last words of wisdom. Linda stands between us and beer.
You want to walk? We'll go to the, no, I'll make it real short. So you ask a simple question to a very complex question. You said, are tools smart enough? And I would say to you, I don't believe in a silver bullet. I believe that there are some tools that we have enough history and experience with that we think they're pretty reliable and we're comfortable using them for most cases. But if you ask me if I have the same confidence, forgive me, do I have the same confidence in certain crack tools that I can say, let's say there's a situation on a pipeline company and they've got some spiral cracks. I mean, cracks in a spiral pattern. And you say, they say, well, we just want to run a tool. I might say, you know, I think you need to follow it up with something else. And you see that we've been consistent in our corrective action orders, that in some cases, if it is a simple corrosion, company says, we know we've got corrosion because we've got despondent coating or we've got this, and that is their threat, and they'll come back and say, we think that MFL is the appropriate way to check this, maybe so. Maybe we're getting closer to assurance and comfort with that. But is there a silver bullet for all types of threats? No, I don't believe so. And maybe we'll go in that way, but I think right where we are now, sometimes we have to follow up with a different type of assurance method. Sometimes we have to have an additional layer of certainty to make us feel comfortable that the integrity threat is being addressed. So I'd say yes to some circumstances and absolutely no to others.
And so if you need that additional layer, is that somehow built into integrity management that you can enforce that?
Yes, it is.
All right,
Yes,
good.
and we have. And we actually had, sorry guys, that's his fault. He asked an additional question. That one's not mine.
I'm paying for the beer, so.
So you remember a few years ago that we had a workshop about, you know, threats and interactive threats. Do you remember the big hoopla about interactive threats? Because what we found was that some companies were going out and finding their threats, but they weren't thinking about what happens when you have two threats that intersect. How do you assess for that? And they weren't putting the pieces together. We had a workshop and a discussion about reminding everybody, hey, you have to look at this. So would one internal inspection tool find two different threats? No, they might not. So you have to constantly be thinking about what are the threats that we're actually confronted with, and are we covering them all to the best of our ability? And Carl, if we go out and we inspect a pipeline company that says our only threat is MFL, we're going to say, really? What kind of pipe do you have? And we're going to have that discussion to make sure they're adequately addressing them.
All right.
Okay.
I asked
Got
all
that-
my
got
hard,
that out, so I
naive,
feel
probing
better.
questions, so now we can go drink beer. Thank you. Let's give these folks a round of applause. The reception starts right next door where we had lunch at 5:30, about half an hour.